Now we're ready to talk about estimating the slope. And this time, we're not going to assume that we've already estimated anything else. We're not going to assume that we've already estimated the residual variance or the intercept. We just have a data set, so a bunch of points that have x and y coordinates, and we'd like to estimate the slope of a regression line. What we're going to do actually is we're going to come at this idea in lots of different ways, because I really want you to develop some intuition for this mysterious expression that we're going to come up with for using the x and y values to estimate the slope. So here's the first way that I'm going to talk about it. Let's take a data set. Here's x, here's y, and let's put some points on it. Okay. So what we're trying to do is find a way to understand how related the x variable is to the y variable, right? That's what we're trying to do here. So how are we going to do that? Well, one idea we might use is going back to marking the sample mean of the x's. So if you take all the data points and only look at the x variable, what's the sample mean? And then the sample mean of the y values, if you look at all the data points and calculate the sample mean only of the y variable, right? Looking at those, and then using those two values to divide the plane into 4 quadrants. That's what we're going to do. Why would we do that? Well, intuitively, we're doing that because I can look at these 4 quadrants and see where the points lie, which ones are in which quadrant, to get a sense of how related x and y are. So in this particular data set, as I've drawn it, there's a lot of data points right here, right? And there's a lot of data points here, but there's not too many data points here or here. And that tells me that there's a pretty strong positive relationship. Right? There's a pretty strong positive relationship because most of the values are in quadrants that are diagonal from each other as opposed to adjacent from each other. Let me draw you a kind of smaller counterexample. Suppose we have x and y, and here's x bar, and here's y bar. Suppose the data points are scattered evenly across the 4 quadrants. So now I might say, hey, the number of data points in each quadrant is the same. That is another way to say, hey, it doesn't look like x and y are particularly related to each other. So once we divide the data up into quadrants, understanding how many data points fall in each quadrant actually is a measure of how related these variables are. So I want to stop there and just say, that actually could be our measure of how related the variables are. If you were making up your own measure for how related x and y are, you could just literally give me a count of how many points are in each of these 4 quadrants, and that would be a way, right? That would be a way to do it. Kind of like when we were talking about variance and measures of dispersion, I said that you could make up your own, and we talked about the MAD or the MAD and different ways to understand how dispersed the values are. It doesn't have to be always a famous method. Same thing here. If you just decided, hey, the way I'm going to understand how related x and y are is to count how many values are in each quadrant, that is a perfectly valid thing to do. It doesn't have a famous name, but that is a perfectly valid approach. So it turns out that the approach that does have a famous name is inspired by this graphic with the quadrants. So we're going to make a little table. So imagine that we're looking at each possible data point, and the first thing we're going to measure is how far that data point's x value is from the mean of all the x's. Okay. And the next thing we're going to measure is how far that data point's y value is from the mean of all the y's. So I want to think about these values, and in particular, I want to focus on when they're positive or negative. So if this difference is positive, what that means is that this data point is over here somewhere, like its x value is bigger than the mean of all the x's. And if I have a positive value here, it means that this data point's y value is over here somewhere. Its y value is bigger than the mean of all the y's. And so this quadrant contains all the points where both of these differences are positive. What if I put a negative here and a negative here? Where are the values that are negative, that have a negative difference between the x value and the mean of the x's and the y value and the mean of the y's? Okay. let me use the same color I did before. That's going to be here. This is the negative, negative quadrant, right? Okay, what else? What's left? Well, I could put a plus and a minus. These are the data points where there's an x value bigger than the average of the x's, but the y value is smaller than the average of the y's. That's these. And then we also have this, the negative pluses. These are the values where the x value is below the average of the x's, but the y value is above the average of the y's. There we go. So now I've managed to label the quadrants using these plus and minus signs. What am I going to do with this? Well, remember, what I'm interested in is to what extent the data points are diagonal from each other as opposed to adjacent from each other, because that's what distinguishes between the two types of graphics that I've drawn on this slide. So how are we going to do that? What do I do with this quantity xi minus x bar and y minus y bar to help me figure out how many points are diagonal from each other and how many are adjacent? Well, here's what we're going to do. We're going to take the product of these two differences, xi minus x bar and y minus y bar. And right now we're going to think about the sign of those products. So if you take xi minus x bar times y minus y bar, literally for a particular data point, calculate those two differences and multiply them together. If both differences were positive, well, a positive times a positive is a positive, right? You knew that. If both those differences are negative, a negative times a negative is also a positive. But if one of those differences is positive and one is negative, you're going to get a negative. Okay. Why would this be an interesting thing to do? Well, this is going to help me count how many data points are across from each other as opposed to next to each other, right? So if I take all my data points and then just report whether this product is a plus or a minus for that data point, by looking at the number of pluses as opposed to minuses, I can figure out whether I have a picture more like the one on the top or the one on the bottom. In the picture on the top, I'd have a lot more pluses for this product because most of the data points are either here or here, as opposed to the opposite. But in this picture down here, below, the data points seem to be equally likely to be in any quadrant, so I'll have just as many pluses or minuses. And that suggests there's a less strong relationship. So now we're getting toward quantities that actually have famous names. This quantity I'm going to define is called the sample covariance. Sample covariance. The sample covariance is equal to the sum of all these products. So for each data point, we're going to add up the difference between its x value and the mean of the x's times the mean of its the data point's y value. Let me say that clearly because my tongue got tripped up there. For each data point, I'm going to add its x value minus the mean of the x's times its y value minus the mean of the y's. I will calculate that product for each data point and add all those up, and then divide by n minus 1. Okay. Why n minus 1? Because that makes it match the sample variance. In fact, it means that if you take the covariance of x with itself, then this actually simplifies to s squared. If that was confusing to you, just pretend I didn't say it. It's fine. Okay, so this is the definition of sample covariance. So now this motivation we have to divide the data into quadrants in order to understand whether there's a relationship has translated into an actual famous quantity, the sample covariance. So the sample covariance is a quantity that's meant to help us understand to what extent there's a relationship between these two variables. Sample covariance can be either positive or negative, right? It'll be positive if there's lots of positive values here. So if there's lots of values in the upper right and lower left, we'll get a very positive sample covariance. If there's lots of values in the upper left and bottom right, we'll get a very negative sample covariance. And if the data points tend to be evenly spread among the 4 quadrants, we'll get a sample covariance close to 0. So that's what sample covariance does, but it also does something else, because we're not just adding up the pluses and minuses, we're adding up the products themselves. So the sample covariance is not only measuring which quadrant the data points are in, but it's also measuring how far they are from this overall intersection of the means. So I'm going to draw my upper right plot a little bit. If I have a data point way out here, well, its x is way bigger than the mean of the x's, and its y is way bigger than the mean of the y's. So not only is it going to contribute a positive value to this sum in the sample covariance, it's going to contribute a very large in magnitude positive value. Now consider a point that's like way out here, right? That's a data point that will subtract a large amount from the sum that's in the sample covariance, right? I'll add a very large negative number, because the magnitude of the value xi minus x bar times y bar minus y bar will be big, but it'll just have a negative sign. So this first value I drew, I'm kind of circling it here, will make the sample covariance more positive. This one would also make it more positive, right? But having a data point way down here would make it more negative. The sample covariance measures the extent to which the data points are in quadrants that are opposing as opposed to adjacent, and also how far those data points are from the intersection of the means, how extreme they are. So now we're going to divide this quantity by something to make it into something else that I bet is familiar to you. And that is the sample correlation. What's the difference between just a regular correlation and a sample correlation? Well, the true correlation is a value you would calculate if you had the entire target population, all the x's and y's, the entire target population. The sample correlation is the correlation between x and y that you calculate from your sample, your data set, which is a subset of the target population. The sample correlation is simply defined as the sample covariance divided by the product of the standard deviations. So here's how I'm going to write it. First, I'm going to write down the sample covariance, 1 over n times the sum over all the data points of xi minus x bar times yi minus y bar. And then I'm going to divide that whole thing by the standard deviation of the x values, totally ignoring y, times the standard deviation of the y values, totally ignoring x. Okay? So that is an important quantity. It is also called R. Let me write that down too. Where should I write it? How about here? This is equal to R, little r. Okay, that's what we call it. The sample correlation. Now, you can see that the sample correlation too is just inspired by this idea to check to what extent the data points are in opposing quadrants as opposed to adjacent quadrants. Like the sample covariance, it also reflects how far the data points are from the intersection of the sample means. And now it's divided by each of the standard deviations. Why do we do that? Well, because R then has to be between -1 and 1. So the advantage of using the sample correlation instead of the sample variance is that now, no matter what the data set is, I can talk about how related the data points are and give you a number between -1 and 1 that you can immediately understand. Like if I say the correlation, the sample correlation is 0.99999, now you understand that the data points are very related to each other. Whereas if I just told you the sample covariance is 0.99999, you'd have to ask me, oh, did you measure in centimeters or inches, right? You have to understand the scale of the data to interpret any particular number given the sample covariance. Just to relate it to the things you've seen already, when we were talking about the variance of a data set, if I say, oh, hey, I'm doing this cool experiment that I've never told you about before, and the variance is 6.2, that doesn't tell you anything because you don't even know what I'm measuring or what the units are, what the scale is of what I'm measuring. Are they inches, are they centimeters, are they pounds? 6.2 doesn't mean a thing if I just tell you that's my variance, right? Same thing with sample covariance. It's measured on whatever scale the data is measured on. But the sample correlation is standardized. You take that sample covariance and divide it by the number of standard deviation, by the standard deviation of each variable, so that you end up with this quantity that has to be between -1 and 1. And now, even if I don't know what your study is about, if you say I'm doing this cool experiment and the correlation between my two variables is 0.9999, now I say, hey, that's really interesting. That's a super strong correlation. And I can realize that without knowing more about how your data is being collected.